A very good afternoon to all of you present here. I am Srinivasa Raghavan from the Department of Materials Science and Materials Testing at the Applied Science University of Kaiserslautern. And today my topic is about evaluation of surface and volume damages under Hcf and Vhcf loading for quenched and tempered steels. So first, let me talk about the aim and the motivation behind the project. Then I'll move on to the experimental setup and the methods that we have used. Then I'll discuss in detail about the experimental results. And then at the end, I'll summarize all the points that we are to cover in this presentation and give you all an overview. So according to the International Energy Agency, the steel industry is a major contributor of carbon footprint, almost accounting to 7% of global carbon dioxide emissions. And thus it is really necessary for us to promote sustainable engineering practices. And that we can do by introducing new developments in material science, by developing new methods in engineering practices and so on. And there are many approaches to sustainability. So this is a very 3R, this is the first model, 3R, and this is a very classic model that we all are familiar with: reuse, reduce, and recycle. And another similar one is circular economy. Here we are talking about slowing down the material flow by designing longer lasting products. And then next we'll move on to the narrowing of material flow by using the lesser material by through lightweight constructions, for example. And then we'll try to avoid scrapping of materials and then reintroducing it back into the material flow, thus closing the material flow. So let's imagine a scenario. I have a product here or a component that is partially damaged, not 100% damaged. And what if I want to use it again? What if I do not want to go through the process of melting it and then investing money, time, and energy in it, and then or scrapping it altogether? What if I can just reuse it? So that is where reuse comes into play. So this reuse approach is an excellent opportunity for material resource management. And this is very relevant for us because scrapping usually occurs even though the end of material integrity is not reached. And it also there's also problems with recycling. We are already the steel industry is already saturated at 30% of recycling the damaged products, and we also have economical ecological issues with it because, for example, a lot of accumulation of precipitates, for example, copper, is an issue in recycling. So how to implement reuse? For implementing reuse, we need to take into consideration the following prerequisites: selection of relevant material areas. What is most relevant to me? Is the surface more relevant, or is the volume, for example? And then development of reliable damage assessment methods. How much damage has occurred, and how can I make sure that the damage is there? And how can I quantify the damage? And development of reconditioning methods. How can I remove the damage so that I can reuse it again? And determination of reuse potential. How much lifetime that I can make use of more after reconditioning. And I also take into consideration the influence of size, geometry, and frequency effects. And then, of course, the statistical models as well. And I also have to take into consideration the fracture mechanics, the damage mechanisms, and I have also do crack modeling. And what if I can put everything together in a model? And this model is actually the main goal of our project, the identification and resolution of these prerequisites. And we are trying to develop an encompassing model, which is our primary goal. So experimental setup, we have used a servo hydraulic fatigue testing machine from Shimatsu. And here we have conducted load increase tests as well as constant amplitude tests at 5 Hertz and at a load ratio of -1 at room temperature. And to monitor the fatigue behavior during the experiments, we have used extensometer, resistometry, that is for measuring the change in resistance, and magnetic Bark-Ozone sensor for magnetic part and aspect, and then IR camera for thermography. And the next part of the set of experiments, we also have used a resonator from Rosenberger. And here we have conducted constant amplitude tests at a load ratio of -1 at a frequency of 260 Hertz at room temperature. So the material that we have used here is quenched and tempered SAE 440 steel. It is widely used in automobile components like crankshafts, gears, and etc. And it was heat treated at an oxidation temperature of 860 degrees Celsius, and then quenched, followed by tempering process at 550 degrees Celsius for 120 minutes. And that is how we get the mechanical properties and the chemical compositions that I have listed here, tabulated here. And the result is a very typical relaxed martensite microstructure that we can see in the in the micrographs. So our project strategy is to start with general generation of SN curve with use of a method called stress life method, and then we are to define the pre-damaged amplitudes at the point till which I can damage it partially. And then we are trying to find out, we are trying to conduct pre-damage experiments in the Vhcf region until half the lifetime. And after pre-damage experiments, we are monitoring the damage. We are trying to quantify the damage using microscopic using NDT as well as microscopic investigations. And then we will think about reconditioning the material, that is removing this removing the damage that we have introduced. By this is done here, the surface damage is removed by fine tuning and polishing here. And next step will be mixed HCF and VSF loading of the reconditioned material. And at the end, we will be evaluating the reuse potential from the experimental results that we have obtained. So I talked about the stress life method. I'll go through it again very briefly. So stress life method is implemented with a combination of Morrow, Coffin-Manson, and Baskin relationships. So here we'll be conducting one load increase test and then two constant amplitude tests. And we'll be putting the data what we have obtained together in a Morrow equivalent plot. And then the next step will be visualization of the material response against the number of cycles to failure. Here we also can see this next step will be taking the data that we have so far and then using it to calculate further coefficients and exponents that we need for calculation of stress life curve. So the first step was to conduct a load increase test. Here we have conducted a load increase test starting at 400 megapascals, and we have increased for each step with 20 megapascals. The duration of each step is 6,000 cycles. And here, for the simplicity's sake, I have just used thermal data for representing the cyclic deformation curves. And here we have a slight increase, the first considerable increase, and that we consider as an estimation of fatigue life, fatigue limit, sorry. And here we have taken the data for each load step, and then we'll be using the data in the further coming steps as well. So next step will be conducting constant amplitude tests. Here we have conducted 2 of them, and then we have taken the data from most relevant points here at the half of their lifetime, and then we have to use it again later. So this stress life equation is actually a combination of Baskin and Coffin-Manson relations put in the Morrow relation, and thus we get the SN curve here, and we can see there is a good acceptance agreement between estimated and calculated fatigue limit. For this case, it's around 448 megapascals. And from here, we also have determined our pre-damage amplitudes as well. So till now, we have talked about the procedure. So now we are going to talk about the pre-damage experiments, and we have carried out pre-damage experiments at 2 stress amplitudes, one at 620 megapascals, another one at 560 megapascals. So the damage before and after pre-damage experiments were also measured in addition to other NDT with magnetic Bargauss noise sensors. And here we see the so-called butterfly curves from the ambient sensor. And we can see the change in effective voltage plotted against magnetic field strength. And the red line is for pre-damaged condition, and the blue line, blue curve is for the initial conditions. And this is also reflected on the temperature curves as well. So this is the initial stage, and this is the pre-damage stage, and both show a correlation. Both show an increase, a proportional correlation. So next, we also try to do microscope investigations to visualize the surface damage. And this is the surface before pre-damage in the initial condition. This is surface after pre-damage, and we also have noticed some microcracks developing as well. So after this pre-damage experiments, we have removed the surface damage that we have introduced mechanically by fine tuning and polishing. So now we are done with the pre-damage experiments. Now we are going to move with the secondary loading. And it is done here at 560 megapascals at 260 hertz. And it is carried out on initial condition specimens as well as pre-damage specimens. So to have a reference. So here we have the graph where we see the number of cycles plotted against the material condition. The green dots represent the specimens in initial condition without any pre-damage at all. And the second one, second set with the red rectangles, it shows the pre-damage specimens at 620 megapascals, and the third one is the pre-damage specimens at 560 megapascals. So we see here we see the cyclic deformation curves for each condition. This one is for the initial condition specimens. So we also can note that the 620 megapascal has almost no considerable influence, no clear influence on the lifetime, but the 560 megapascal pre-damage specimens can exhibit actually an increase in lifetime. So these are the cyclic deformation curves for the second condition, and this is for the last condition, which is at 560 megapascals. And we also try to compare what is the difference between the experiments at 5 hertz and 260 hertz. So this is not a direct comparison. This is just for representation. And this is, you can see that the initial condition specimens have a very comparable output. And the specimens at 620 megapascals show a different trend as well as does these with the blue lines, which are preloaded at 560 megapascals. So I'll come to the summary first. And we have started with generation of ascent curves. And through that, we have determined the pre-damage amplitudes and then the extent of pre-damage that we are to introduce to the specimens. And then we have carried out the pre-damage experiments till half of the lifetime. And then we have assessed the damage that we have introduced into onto the specimens. Then we have loaded for a second time the steel at 260 hertz. And in the future, we plan to systematically expand our analytical and ambient investigations for better quantification of the pre-damage influence. And we also plan to do Vhcf loading of, the secondary loading in Vhcf region at 1000 hertz. So our project goal ultimately is to transfer all the data that we have obtained into an into an overreaching model that can be used for design of components made from reused materials. I would like to thank the DFG German Research Foundation for the financial support as well as the technical support and my project partner, AWDH Aachen. So thank you, all around.